Welcome everyone to our Campus Climate Action Speaker Series webinar. We're excited to share with you today in this series. You can go to the next slide, Ellie. We've framed our series on how MIT can highlight ways that we can address the world's climate crisis by dramatically reducing our own carbon footprint. Throughout the history of MIT, we've always had a central utilities plant. You can see the picture of the original design of the building with the central utilities plant there, first fueled by coal, and then every decade a new energy stream got us more efficient and more better fuels over time. So as we transition off of natural gas to the next transition, we hope to achieve our net zero goal by 2026 and looking towards 2025 for a zero emissions future. So this series and this talk will be hopefully a wonderful opportunity to hear about how MIT is moving our district energy system to a zero carbon future by 2050. So I'd like to introduce Jacopo Buongiorno, who is a Bastille Energy Alliance Professor of Nuclear Science and Engineering at MIT, and is a member of the U.S. National Academy of Engineering. He's also the Director of Science and Technology of the MIT Nuclear Reactor Laboratory and the Director of the Center for Advanced Nuclear Energy Systems. Jacopo teaches a variety of courses in thermal fluids and nuclear reactor engineering. He's published over 110 journal and articles in this area of reactor safety and design, two-phase flow and heat transfer, and nanofluid technology. For his research work and his teaching, he's won several awards, and he is a member of the accrediting board of the National Academy of Nuclear Training, a fellow of the American Nuclear Society, including service on its special committee on Fukushima in 2011 and 2012. He's a member of the American Society of Mechanical Engineers and past member of Naval Studies Board, also a past member of the Secretary of Engineering Advisory Board Space Working Group, and a participant in the Defense Science Study Group. We are thrilled to welcome Jacopo to the Decarbonization Forum and hear about this exciting prospect of microreactors technology here at MIT.
So thank you very much. I hope you can hear me well. Thanks for the introduction, and thanks for inviting me, of course. Always exciting to talk about these topics. I'm going to try to share screen here. Please confirm that you see the slides, especially now that I put it in slideshow mode.
Yeah, you probably want to swap the display settings because we can see your notes.
So that's going to be a challenge.
Right at the top of the screen where it says display settings, just hit swap, Jacopo. Yeah, there you go.
Nice. I just learned something new. Fantastic. Okay. So as Vaso said, we're going to talk about microreactors, nuclear microreactors, for the purpose of helping decarbonize our campus. And there is also a research mission that I'll try to highlight. So I'm not going to dwell on my bio. Vaso just introduced me, other than saying that I've been learning, thinking, working on nuclear energy for over 30 years, and I've seen a lot of ups and downs when it comes to support. I have to say, at the moment, for a variety of reasons that I'm about to enumerate and explain, the support for nuclear in the US and globally is probably at an all-time high, certainly in my lifetime. So what happened in the past few years that has sort of put wind in the sails of nuclear, as well as other clean energy technologies. The first very sad event, of course, the invasion of Ukraine, resulted in what I refer to as an energy security epiphany. A lot of countries have realized that being at the strongly dependent on other countries for energy imports is not in their best national security interest. And so energy technologies that don't require fuel, like solar and wind, or require very little amount of fuel to be imported, like nuclear, become attractive in that context. Similarly, of course, the conversations about climate change, which culminate in this annual meetings, conferences of the parties, or COP. For the longest time, nuclear was sort of excluded from the conversation, but starting back on COP26, which took place in Scotland 4 years ago, nuclear has been invited to the table, and it's now routinely included in discussions about climate policies to basically clean up our energy system. There have been an important pronouncement by many countries, including the US, a pledge effectively to triple the global nuclear capacity between now and 2050. And importantly, going with that, excuse me, with that pledge, an expression of interest by 14 leading financial institutions, these are large investment banks, declaring their readiness to basically finance nuclear projects. China is undergoing the largest expansion in nuclear capacity in history, 150 gigawatts, a lot of power in 15 years. They started 7 years ago, so they're roughly halfway through, and they're on track. There are 63 new reactors under construction worldwide out of 440 that are already in operation. A bunch of other good things have happened for nuclear. I'll just dwell on these last two bullets here. Here in the US, there is a strong interest in using nuclear and other energy technologies to basically support the expansion or the growth of AI and data centers that implement the algorithms that AI uses. And so the figure that I read is that between now and 2030, so maybe the next 5 years, the US will need some 50 gigawatts. That's additional capacity to basically fuel this AI growth. And just to give an idea, currently the grid, the United States grid is 500. So that's about a 10% enhancement in average energy generation just to support AI. And so in that context, there is interest in using nuclear to meet those those goals with no emissions. All right, so now focusing on campus, I think, Vasu, you already alluded to this in one of your slides. College campuses require a lot of energy. Simplifying a little bit, I like to say college campuses run on steam. So in the past, and unfortunately still in the present, we burn a lot of fossil fuels to generate that steam, either natural gas, coal, or oil. The unfortunate consequence of that, of course, is CO2 plus NOx and SOx and some particulate pollution. But what you get out of burning these fossil fuels is steam. You can use steam through a turbo generator to make electricity. You can use that steam through a pipe network to basically heat your buildings. And you can also direct some of that steam to absorption chillers and actually get chilled water. The idea that we're going to discuss here is to essentially replace the burning of fossil fuels with a nuclear reactor. And the nuclear reactor is a heat source, so you do get heat that then you can use to produce steam and then do the same things that you did with the with the fossil fuels, but without emissions. All right, so just to explain a little bit different categories of nuclear reactors that are out there. This can get confusing, so I always start with this slide. The vast majority of nuclear reactors that are in operation at the moment around the world, including the United States, is what we call large light water reactors. The word light water simply refers to the fact that the coolant circulating within the reactor core is H2O, so that's water. But the emphasis here is on large. So these are large machines producing order of a gigawatt or more, and they're connected to the grid. They are pretty expensive to build, and they take a lot of time. And you see at the bottom there a bunch of companies that build these plants. There is now interest in what people call small modular reactors. They should really be called smaller modular reactors because they're still fairly large in physical size as well as power output, between, let's say, 70 and 300 megawatt. The range there is because there are a lot of different designs. And again, you see a number of companies that are active in that space at the bottom of the slide. And what I really want to focus on today is micro-reactors. And that's because they are in a range in terms of power output, that's electric power, let's say 10 megawatts or thereabout, which is more consistent with the needs of a campus like MIT. And again, you see there a few companies that are active in developing these technologies. Okay, so what are the essential features of these microreactors? Unlike large reactors, which essentially require a very big construction site, thousands of workers on site, these are meant to be mass fabricated in factories and then transported out to the site in more or less standard containers. You see an example on the top right there. They would be co-located with the end user. In this case, the end user would be our campus, so they would be located here. They would not be connected to the grid and far out. They are meant to be more or less plug and play startup. Typically for large reactors, once you have built the plant, it takes several months before you can actually connect it and become commercially operational because of testing and sort of verification that the system behaves as it's supposed to. Here, these are pre-tested in factories, and basically the assumption is that it would take a couple of weeks before you're up and running. There are small systems. They produce only a modicum of power, so you cannot afford to have a lot of operators, and so they're being designed to be semi-autonomous. Basically, if there is a change in the load, the reactor can follow the load without any external operator intervention. As I said earlier, a reactor is a heat source. You can get heat if that's what you want. You can get heat and power, or you can get just power. That's pretty versatile. They're small enough that they do not require water to be cooled, so they don't need to be close to a river or the ocean. They just use atmospheric air, so they're dry cooled. The refueling of the fuel, the nuclear fuel, is done off-site. So just like you get the reactor in on a truck, you send the spent or the exhausted reactor back to a central facility where it's refueled, and that either sent back to you or sent to a different customer. The point is that there would be no need for handling spent fuel, which is what people call waste, radioactive material on site. They're passively safe. I think I have a slide that describes a little bit more what I mean by that in a minute. And the investment and schedule associated with the deployment of these systems is expected to be drastically smaller than for large reactors. As I said earlier, a bunch of companies out there, not all equally credible. The three that I mentioned here are the ones that lead, in my opinion, in terms of capabilities and again, credibility because of the experience they have. Westinghouse being one, BWXT, and X-Energy another one. All right, so nuclear is a very compact energy source. Here, just to give you an idea of scale, that green rectangle would be roughly the size of a 10 megawatt nuclear microreactor, and that's how it compares to a nominal 10 megawatt either solar field or wind turbine. In fact, it's even better than what is shown here because for a reactor, nuclear reactors operate with high capacity factors, so effectively you get even more power than what's shown for the alternatives there. Without getting into too many details, as I said earlier, there are several companies here and different designs. The one that we ended up focusing, and I'll explain why later on, is Westinghouse's eVinci. You see it up there on the top left. It has a horizontal layout. The central part of that drawing is what we call the core. That's where the uranium fuel is. That's where the heat is generated. And then this particular design, the heat is taken out not by a circulating coolant, but by heat pipes. So these are sealed pipes with a little bit of sodium within each pipe. And that sodium evaporates at one end and picks up the energy in the core. And then it condenses at the other end and gives it off to a working fluid, which then goes to a turbine, and you get the electricity that way. So it's pretty simple, as essentially no moving parts in the reactor itself. Of course, turbines and compressors are needed to move the air over that heat exchanger that picks the energy from the core. I mentioned transportability. So for that particular design, the system essentially comprises these four containers. Those are that's the equipment that the reactor needs. On the left is the reactor itself. In the middle is the turbo generator. Then you have the instrumentation and control module, and then some support equipment. These containers are more or less standard. They're supposed to travel on road. The one with the reactor is about 100 tons, so that requires a special transport, but still is road transportable. Now, this is what an actual site layout may look like. So yes, the components come in those four containers, but there is more to the site than just those components. And so again, focusing maybe on the Vinci there for a 2-bay layout, which in that case would basically accommodate 2 reactors. You can see there you got the reactor in the middle, you have the turbo generator, then those blue boxes are the instrumentation and control modules, and then surrounding each reactor you have a little what they call the enclosure, which is made of prefabricated concrete. And that's basically there as a shield building, both as radiation shielding, but also as a shielding from external missiles, whether it's an airplane crash or some act of sabotage. You want to protect the reactor that way. Now, this idea of microreactors is not actually new. Back in the 60s, the US Army deployed tiny reactors that were mobile. You can see a couple of examples there. They were very low power, 400 kilowatt, 200 megawatt electric, 2000 megawatt, excuse me, 2 megawatt electric. Now you were talking 5, 10, 15 megawatt, so a little bit bigger. But what really has happened since the 1960s is that a whole suite of technologies, in many cases unrelated to nuclear, have become mature and now can be used in a 21st century design of a microreactor. I'm referring to things like compact gas turbines, but also components made with additive manufacturing, of course, advanced controls and instrumentation using machine learning, robotics, et cetera, et cetera. And then last but not least, there are a lot of synergies when it comes to the development of the microreactor technology with other government programs. The Army still is interested in these machines for forward operating bases. NASA has a microreactor development program for nuclear power for both surface, like on the surface of the moon or Mars, as well as for propulsion. And so a lot of the materials, fuels, methodologies that are developed in those programs can be applied to microreactors for the civilian sector as well. Okay, I mentioned safety earlier. The trend within the nuclear industry in the past 30 years has been to go to what we call passive safety. So in traditional large nuclear plants, the basic safety functions of shutting down a reactor, maintaining cooling long-term, and then containing radioactivity were typically achieved with energized components, things like pumps, which require motors, which require either a connection to the grid or diesel generators. Well, for example, the Fukushima accident has shown that if you don't have available pumps or diesel generators, etc., your safety systems cannot function, and then you get in trouble. So the trend has been for the longest time to go towards a safety approach that does not rely on energized components. So does not require pumps, does not require diesel generators, and also minimizes the need for external intervention by operators, which should reduce the risk of human error. So you put that together with some inherent characteristics or features of the design, things like fuel type that is very robust and doesn't, it can take very high temperatures without releasing radioactivity and things of that type, and you get a very robust safety profile. What's the implication of this? Well, the traditional sort of accidents like TMI, Chernobyl, and Fukushima are literally eliminated by design. That is not to say that you cannot have accidents. Every time you have an engineered system, you can have failures and malfunctions, but the consequences of these accidents now in these new machines would be very, very different, to the point that you can basically limit what we call the emergency planning zone to site boundaries. So even under the worst possible case, there is no need for people to evacuate or to take iodine pills or things of that type. So in that sense, I will say these microreactors are pretty similar to our own research reactor here on campus. We've had it for 60 years. It's in, has some of these similar characteristics, and the emergency planning zone for the existing research reactor is essentially the site boundary. All right, so before I go back to what we're going to do or what the project looks like on campus, let me just give you an example of how these microreactors could be used in the marketplace. So unlike large reactors, which are meant to be connected to the grid, and then the electricity, of course, is propagated wherever is needed, these microreactors make sense only if you collocate them with the end users of your energy. So the example shown here is a mine. suppose you have a mining site. Mines actually require a significant amount of energy, mostly in the form of electricity. So the first thing that you could do if you deploy a bunch of micro-reactors at a mine, it could be to electrify mining and reduce emissions associated with the mining operation. But you don't have to stop there. You can process the ore that you get from a mine in situ, on site, using, again, energy output from the micro-reactors. And if you're in the business of making steel, for example, you could use the Boston Metal style molten oxide electrolysis. That's Professor Saddleway's invention to basically make clean steel on site. The only input that is required is the raw materials, the ore, as well as the electricity and heat, which would be provided by micro-reactors. So now you got clean steel, which means no carbon emissions. And you don't have to stop there. You can finish it. You can sort of turn the clean steel into a architectural alloy or aerospace alloy. Now that's a high value added product, and so now you're selling something that fetches a much higher price in the marketplace. So the features of a site like this would be, first of all, you're eliminating or drastically reducing the need for a lot of energy transmission infrastructure, literally transmission lines or even pipelines if you're thinking about natural gas. You don't have to pay a lot of middlemen because you're doing everything at one side. So that sort of shortened the markup chains. You have a larger margin. You can deploy this capacity in smaller increments, one micro-reactor at a time, coupled to one molten oxide electrolysis cell at a time. And that's good for cash flow. And finally, you can say with a straight face that what you're making, whatever it is, whether it's steel, glass, food, whatever it is, that comes out of this site is carbon free because all the energy input is from the nuclear reactor. Now, that's an example of the mine. In principle, you can apply these across all sectors of the economy. You probably start with applications where the competition is very expensive. So think about any remote sites where the competition would be diesel generators, the electricity from diesel generators. Those would be prime first mover applications. So military bases, microgrids, we talk mining sites, in space installations, and then as your costs come down, as you deploy more and more of these machines, then you can start maybe penetrating more commoditized markets, district heating, desalination, put these reactors on cargo ships for propulsion, and et cetera, et cetera. Now, as I said, it's not an entirely new technology, but the new designs are new, and there are some key uncertainties. Mostly are not of technical nature. You see here sort of a list. I don't have time to go over all of this, but don't expect these reactors to give very cheap electricity or heat. They don't. Typically, large reactors are more efficient in that sense. Smaller reactors cost less, but in terms of cost per unit energy, they tend to be a little bit less efficient. So that's what I mean by these economies of scale. The fuel that is being used is uranium, but in the form and enrichment that are required for these micro-reactors, the availability of the fuel and the cost of the fuel are going to be questions. They're going to be certainly higher than the cost is going to be higher than traditional reactors. And then there's a bunch of things related to how do you transport a fully fueled reactor from and to the site. What does that refueling facility looks like? I mentioned autonomous operation, how you're going to license these reactors in an urban environment, and lastly, how you secure it, including cybersecurity. But really, the toughest nut to crack is the physical security. Okay, so now coming to the campus itself, this is an example of our load for electricity on top over a course of 1 year, and for steam at the bottom. So you're looking at a sort of a floor of roughly 20 megawatt for electricity and a floor of a little bit above 100. These are pounds per hour of so thousands of pounds per hour of steam. And so I think, Vaso, you mentioned this in the introduction. Of course, there is a portfolio of technologies that are being considered to decarbonize campus. And when it comes to heat specifically, the three that are being examined, and this could be used in, by the way, in combination, they're not necessarily alternative, are electrification using heat pumps. So then basically you're relying on the grid to get your carbon-free electricity, and you use that electricity to drive heat pumps to get the heat that you need. You can improve the efficiency of the overall energy system on campus by having some heat recovery system. You can do our nuclear micro-reactor, that is the focus of this talk, and also there is a discussion about drilling holes across campus to basically get to hot rock, and that's called advanced geothermal. So what is the value proposition in this context of nuclear? Well, listed here. Resilience, what I really mean here is it's essentially 24/7, 365 days energy source. So it runs all the time. Capacity factors for nuclear reactors on the grid average in the United States are 93%, which is astronomically higher than any other energy source there. So they're pretty reliable machine. As we said earlier, no emissions. Capacity factor availability is what I just said. Quality of resource and heat. I mentioned this already a couple of times. You can get heat at fairly high temperatures. That's what required. I think for our campus, it's not very high temperature requirement, but these reactors can give you the steam at the temperature that is needed here, no problem. Base load and dispatchable. So yes, they run best when they are 100% power flat out, but these micro reactors in particular are being designed to follow the load. So you can use them either as base load, or if at times when the load goes down or up, you can follow it. I'll talk a little bit about the research piece of this. I think it's going to be key that this is not perceived exclusively as, okay, we're doing something for the energy picture, but also that there is a research and education mission. I'll talk about that in a second. And then lastly, of all the energy sources that you can think of, this is by far the most compact for the reasons that I showed earlier. So what does the project look like? It actually started back in 2023 as a collaboration between MIT and the firm Burns and McDonnell, working with our folks here in the facilities group. We immediately thought, okay, this should be integrated with the existing utility system. So you really treat it as a heat source, as a steam source, and then the rest of the system across campus stays the same. So you could slot it in without excessive cost. Location, of course, is a very important question. You see here a map of Massad and Albany Street. The lot that is crossed out there on the left is where we have our existing research reactor, and the two most promising locations for this are the two lots across from Massad, the parking lot there, which is smaller, and then the 1 acre and 10 lot there. So the main output of that project with Burns and McDonnell was a fairly detailed evaluation of all the micro-reactor technologies available out there, and there are a couple of dozens. I only mentioned 2 or 3, but there are many more. So Burns and McDonnell did a very good job of systematically going through all these technologies, and they ranked them for readiness, power output, likelihood of being licensed, cost, et cetera, availability of fuel. And basically, they selected Westinghouse's eVinci. And as a result of that, we added Westinghouse to the team just a few days ago. I think the contract that was approved. And so now the team is MIT, Burns and McDonnell, then Westinghouse. And now we start a real feasibility study for one of these 2 lots, or maybe a combination of these 2 that you're seeing over here. So that's the energy piece. Could we do research with this machine? Absolutely. I'll just say from a strategic point of view, it is important that we do research, not just because that's part, of course, of the MIT mission, but also because in terms of getting US government help with licensing of the reactor, with offsetting or defraying the cost of the fuel when the reactor has to be refueled, it is important that it does have a research mission that is not only run as a commercial facility. But what research are we talking about? Well, we already have a research reactor on campus. That reactor is used as an irradiation test bed. So in the current reactor, we introduce capsules with either materials, fuels, or sensors to basically see what the radiation field does to those materials. That's not what we're talking about here for this new reactor. This would be a test bed, not for irradiations, but for example, innovative control approaches. So there is a lot of interest in this question of autonomy. We have if we end up deploying this reactor on campus, we can clearly test our advanced control algorithms and approaches on the reactor there. Same goes for sensors and instrumentation. It's also an energy source, as I mentioned many times, pretty versatile. So to the extent that there are faculty and students interested in demonstrating generation of clean hydrogen or synthetic fuels or steel or cement using some new process that is being researched at MIT, that is an energy source that would be available and it would basically have no emissions. Another one of interest, of course, demonstrate you could use micro-reactors for direct air capture of greenhouse gases or CO2. Part of the process of deploying, of course, is licensing it, and this would be licensed in an urban environment. So it would also, it's not strictly research, but it's sort of shown how you can license micro-reactors in urban environments. And then last but not least, the educational value of this is kind of obvious. If you have this machine on campus, you can clearly train our students as nuclear engineers in design and operations of these advanced technologies. Okay, so what does the project consist on, the feasibility study that we're launching in? A bunch of things. I'm not going to read through all of this. I'll just say, of course, for all nuclear projects, you got to look at what we call external hazards. It's a pretty long list shown here on the right before you can go to the regulator and sort of request a license. So these are things like that particular area, that block of campus, is it going to be susceptible to climate change? How is that going to change the local conditions or underground water, things like that? Is there any critical habitat? I don't think that's the case on our campus. Things related to earthquakes or are we close to explosive manufacturers? Some of these categories don't apply, others do, but we'll have to be systematically going through all of this. Number two, transportation to site. That's, as I said, it can go on road, it can go on rail. We're fortunate to have that railroad that actually goes pretty close to the site, so that could be a way to bring in the reactor and then send it out for refueling. We need to look at how long a spent reactor, an exhausted reactor, would stay on site before it's shipped out, and where is it put? And then things of, okay, we have the technology is being developed now. How long is it going to take before we can actually use it? So I think this is the last slide I have before the conclusion. So a notional schedule of what this project could look like. We are here at the beginning. That's still a feasibility study, but we feel strongly that we should reach out to the regulator now, not with an application yet, that's premature, but with pre-application engagement with the regulator here that I'm referring to is particularly the NRC, but of course there are other stakeholders at the state and city level that should be engaged as soon as possible to make sure that we cover any questions and any issues that might emerge. The schedule here, without going into details and some of the acronyms there may be obscure, must proceed also in parallel with the demonstration of the technology, which will happen first at the E-Vinci Westinghouse, will happen first at the Idaho National Lab in 2027. And once that's demonstrated, the Idaho National Lab will be ready for a license by the NRC, and that's basically the time when we'll in principle when we can apply. Oops, I lied. There is another slide. MIT is not alone in this. There are other campuses around the United States that are considering this, typically with different technologies, but in one case, Penn State with the same technology, E-Vinci. This was announced just a couple of weeks ago. And so, good synergies here. What we learn and what they learn, this should be shared. We're not in competition in here. It's, it's not a commercial activity. And so I'm pretty sure that we can get, good information from those. All right, so takeaways, I talk about these portable plug and play micro reactors. Hopefully I convince you that it's an interesting technology. Could be used beyond campuses, commercially this markets can be pretty large. It is a carbon-free source of steam, you can do electricity, heat, chilled water, and at MIT we'd like to use it primarily in the heat on the heat side, and then as I mentioned earlier, of course, there are some uncertainties. I'll leave you with this. So the team, MIT and Burns and McDonnell, actually visited the eVinci Technology Center in Pittsburgh earlier this year. And here you see a full-scale mock-up of the reactor core. So these hexagonal objects that you see here, those would be the fuel assemblies. Within those fuel assemblies, you have the fuel, and then you have those heat pipes that take the heat out. This is being tested now with electric heating, not with nuclear heating in Pittsburgh, and then this or the similar system will be tested with nuclear heat, basically as a critical reactor at Idaho in 2027, as I said. So with that, let me stop and see if we got questions. Back to Julian Vaso.
Yeah, Jacopo, first of all, thanks so much. And thanks everybody for joining us. And Jacopo, just want to point out, first of all, also just thanks for being one of our people that have worked, one of our faculty members that have worked so closely and diligently with our team for so many years to really engage the campus as a test bed. So we just want to make sure those who've joined us today, that's what you're hearing today, is how, if anybody's going to understand the application of this technology to a campus, it's going to be working with Jacopo to then inform all of our peers around the country and globally who are asking the same question.